getting into these first five problems. I'm not going to go through all of them. In fact, I'm really just going to kind of do one and talk about another. Because you've seen problems like 1, I feel like number 2 is pretty simple. You would just distribute the x. And what you would do in 3, we're going to do in 4 anyway. So let's look at 4. If I have these 3 factors, how would I multiply factors that look like this? What is that method called? FOIL. Okay, now I'm going to just multiply the first 2. So I'll have 6x squared minus 4x plus 3x minus 2, and then combine those middle 2 terms. Okay, so I've multiplied 2 linears to get a quadratic, and now I'm left with a quadratic and a linear. And so how do I multiply something that looks like that? Okay, it's the idea of FOIL. It's not exactly FOIL, because FOIL is that acronym that is specific to 2 binomials. Okay, 2 factors that have 2 terms, as opposed to a trinomial and binomial. But it's the same idea. I'm going to take the 4x and I'm going to distribute to all 3 terms. And then I'm going to take the negative 3 and I'm going to distribute it to all 3 terms and combine all my like terms. Okay, so if I take that 4x, I've got 24x cubed minus 4x squared minus 8x. Then I'd take the negative 3 minus 18x squared plus 3x plus 6. And then I would go through and combine my like terms. On these problems, obviously, as you can tell, you're going to have quite a few terms. So if you're one of those people that you do the different shapes around similar terms, that is a good practice to continue to do. So I've got my x squareds, which is negative 4 minus 18x. Or minus 18, sorry. My x's, I've got negative 8 plus 3, which is negative 5x. And then I've got the 6 that's all by itself. Okay. Questions on that? And it is a lengthy process, and if you're someone who likes to do box, if you prefer to do the box method, you still can. And I'm not a big fan of box, but the bigger the factors get, okay, if you have a trinomial, the more of a fan I am of it. And so you'd have you have 6x squared minus x minus 2. You'd have 4x minus 3. And you would just multiply everything in there. Okay, it's like a small multiplication chart. So if you would rather do that than all of this, feel free to. Now going to 5. How many of you attempted 5? Raise your hand if you attempted 5. Okay. How many of you got this answer? Raise your hand. Okay. Whenever you have that set up, and with the way it looks, it is a very, very, very common mistake to just cube the x and cube the 3 and think that's it. Unfortunately, it is not that easy. Okay. If you remember, whenever we talked about taking the vertex form, and converting it to standard, the first thing we did was expand that. Okay. So if you're given one of these problems that looks like number 5, the first thing you need to do is expand it out to 3x minus 3's. And then you would do exactly what we did there. Okay, so make sure that you don't make that mistake of I just got to cube each one of those terms inside and that's what I get. Any questions on any of that stuff? Fabulous. Alright, coming down to this problem right here. So we've got these equations again, 18 minus 2h, 12 minus 2h, and then just h. So I've got 3 linear equations. So we want to find in standard form what that cubic function would look like. So I'm going to do to this equation what we were doing to those examples up top. Fortunately, this is going to be a little bit easier because that first factor is just h. It doesn't have anything else in it. So first thing I would do is I would multiply those two to find the product. And whenever I do that, I end up with 4h squared minus 60h plus 216. And then, Taryn, what would I do with that h to get the cubic the cubic equation in standard form?
Multiply it with the 4h squared.
Multiply it with just the 4h squared?
Well, and the rest.
Okay, so distribute it in. So I've got 4h cubed minus 60h squared plus 216h. Okay. Real quick, just to talk about this because this gets brought up quite a bit. If that equation right there is given to me like it is here, and I want to look at the graph, can I put that equation into my y equals screen in the calculator and it gives me the correct graph and table? Yes or no? Yes. Okay. It does not matter the form that it is in, and that's a common misconception. If I put this equation in to y1, this into y2, and this into y3, they're all going to give me the same graph and same table. Okay, it does not matter what form it is. You can still put it into y equals. Okay? Because of that, just so that we know that we can, and because last A days or B day the settings on the calculators may be different. Real quick, I want everyone to do second plus 712 because we'll have to change the windows and the windows may be all out of whack. After you do that, I want you to go y equals, and I want you to put this equation as it is exactly, except for put x instead of h, into y equals. And we're going to use that here in a little bit, but we can go ahead and take the time to put that in the calculator right now. So looking at this, we're going to talk about just cubic functions in general, and on this exact one, most specifically about the parent cubic function, which is just y equals x cubed. Okay, so make sure that we need to make sure that we identify some characteristics of it. I mean, it increases from left to right. You've got the little part in the middle that kind of curves around the origin. Any little thing that looks, that kind of separates itself from other functions such as linear or quadratic, we need to take note of it. So on the increasing part, it goes up from left to right, or you can put up and to the right. We'll kind of talk about a little bit of that towards the end, especially about in behavior. Right now on in behavior, I just want you to put that it is going down and up, and we will clarify that on the next page a little bit more. Okay, domain. The good thing about the domain on all cubic functions is it is going to be negative infinity to positive infinity. Good thing about the range, it's always going to be negative infinity to positive infinity. So do not put anything other than that when asked for that, when asked for domain and range. We will talk later in the notes, we'll talk about a problem that they could ask that would change the domain and range though. Looking at the x-intercept, what would the x-intercept on this be? 0, 0. What is the y-intercept? 0, 0. Some critical points, and by critical points it means a few points that you could easily graph. Okay, that you probably need to know how to plot on the graph, and whenever we get to that graphing lesson, we'll focus on these. But you've got 1, 1, negative 1, negative 1, and of course that 0, 0 on this graph specifically. This parent cubic function is symmetric around the origin. Okay, whereas whenever we talked about quadratics, it was symmetric around what we call the axis of symmetry, which is a vertical line. So it was symmetric around a line. This one's symmetric about the origin. What that means is if you have a certain point, 1, 1, you can change the signs of both of those x and y values, and you also have that point. Okay, so you would have 2, 8. That also means you'd have negative 2, negative 8. If we took this and we did the negative x cubed, that means if I have the point negative 1, 1, which means I didn't graph it very accurately here because it doesn't go through that spot. If I have the point negative 1, 1, I'm also going to have the point 1, negative 1. If I have the point negative 2, 8, that means I'm also going to have the point 2, negative 8. Okay, so I'm just changing the signs of both the x and y value. So on this, you know, and that makes it a little bit easier. On quadratic, we've had to find the axis of symmetry. To find 2 points symmetric to each other. What's the distance from here to here? It's also the distance from here to here and all that stuff. Okay. So let's go down. Talking about the planar box stuff as well. So whenever we graph this, which let's go ahead and do that. So you already have the equation in there. So if you would hit window, we have to adjust the window quite a bit so that we can see this graph. X max, I want you to leave at 10. The X minimum, I want you to put at negative 2. The Y max, I want you to put at 300. And the Y minimum, I want you to put at negative 300. And then go to your graph. Okay, so we all have this graph. What are some key characteristics? What you think? Obviously, you haven't seen many of these kind of graphs. What are some key characteristics that you think are happening in this graph? Okay, it goes through the origin.
It has 3 x-intercepts.
3 x-intercepts. What else? With this, and we haven't talked about it much, obviously, because this is the first lesson we've had on this stuff. Would this graph be considered increasing or decreasing? Increasing. And we're going to talk about that towards the end. And I understand what you're saying, because it's going up and it's down and it's up and it's... Okay? All that stuff. But whenever you look to see if it's an increase or decreasing graph, the best way I can explain this is kind of look at the big picture. Okay? Which means if this is going down forever, eventually, even though it curves and all that, eventually it's going to go up forever. Okay? So it's an increasing... considered an increasing graph. Two other things that we need to point out is you're going to have some points that are called the relative max. And this one is it's the part that looks like it's kind of the vertex of a parabola, and it's labeled on there 2.35, 228. And then you have the relative min, which is not labeled on here, but we'll say it's, I don't know, 7.5, negative 75. Okay, and I'm looking at this point down here. Okay, so all things that you need to notice. Okay, it's an increasing graph. Now we've got 3x intercepts, that's new. And so whenever on this next question it says what is the maximum volume of the planar box? So what would be the maximum volume of the planar box? What do we think? Just by looking at that graph. Do what, Abby? 228. And that is with a height of 2.35. Now, a big part of cubic, and we saw it a little bit in quadratic, but it's going to be even more so in cubic. And going forward, especially you who, if you're choosing this route, if you're going to pre-cal, you will see it in there as well. You have to be able to look at a graph and determine what part of the graph or what part of the data makes sense in this situation. Okay, what is the y-axis representing on this? Volume. So, does this part of the graph make sense? What are all these numbers? The red line I just put on there. All those are what kind of numbers? Negative. Can you have negative volume? No, it doesn't make sense. So if we're answering questions about the planar box, for lack of a better word, we need to ignore that part of the graph. Does that part of the graph make sense? No. Why? It's negative. Can't have negative volume. Doesn't make sense. Okay. Let me put that one in a different color so I can kind of split up this graph to explain something. Does that part of the graph make sense? If I keep following that part of the graph up, that part of the graph is going to tell me that the maximum volume is going to be what? Does that make sense? No. Okay? So you kind of want to look at it in chunks as it goes through the x-axis. So I've got 1, 2, 3, 4. Okay? And you kind of look at it and see, okay, what parts of that make sense and which parts of it does not. On this specific one, if we are answering questions about the planar box, we're looking at that part of the graph and only that part of the graph. So what is the domain? If I just asked you, what was the domain of that graph? We're not saying anything about the planar box. I just said, here's an equation, what's the domain? What would it be? Negative infinity to positive infinity. What would the range be? Negative infinity to positive infinity. Okay? Now, if I throw the word, what is the reasonable domain, and this is what changes domain and range. What is a reasonable domain, and what is a reasonable range? When I throw that word in front of domain and range, it changes everything. Okay? What part of the graph is reasonable? The one that's in the orange box up there, correct? So I'm just finding the domain and range of this part. So what is the lowest x value there? 0. Remember, x is representing height. Is it reasonable that you could, or can we have a height of 0 on this? Yes. Okay, that's whenever I talked about having that. Someone just goes in and buys a flat piece of copper. It's not likely, but it is a possible outcome. What is the highest x value? 6. And then the range, what's the lowest y value of that area? 0. What's the highest? 228. And I'm putting brackets around both of those because they can be equal to those values. What do the x-intercepts represent? And I don't mean when the graph crosses through the x-axis. Within the context of the problem, what do the x-intercepts represent? Eve. On an x-intercept, what value is always the same? The y. What is it? 0. On this problem, what does the y represent? Volume. So what do the x-intercepts represent within the context of this problem? Kind of, yes. Somebody else? You're around the right area. Do what? It represents when the volume is what?
0.
Okay. So the x-intercepts, they represent the heights. That's what the x value would be. The heights that give you a volume of 0. Alright, so going down to this next problem where it talks about the Stonebriar Country Club. They ordered a particular planar box. They want it to have a volume of 100 cubic inches, but they did not specify the height. So that means that there might be a couple different dimensions that are going to fit this. It says determine the dimensions Acme can create to fill this order. So just a minute ago we were talking about the volume being 0. And it was every time that it crossed whenever y was 0, right? Correct? The x-intercepts? We all agree on that? This is yes? Right here, Mandy, this is yes? You agree? I knew you would. Okay. So, whenever it crossed 0, that's when the volumes were 0. They want volume of 100. So that's going to be whenever this graph crosses what? 100. Okay? So what we can do is we can put a line on the graph at y equals 100. Okay, I'm kind of working down here now. This is the same as that, just a lot smaller. We can put a line at y equals 100. And we can go through there and find those x-intercepts. Now, I just want you, so I want in y2, I want you to put 100. And I want you to find those two x-intercepts and see what they are. I want you to round to 2 decimal places, please. Yes, ma'am. That's going to give you a straight horizontal line at 100. Okay, so Tara, in that first intersection point, what did you get for that one?
0, 100.
Try this one. Try that again. Did somebody get something different? Carolina?
I got
0.54. Okay. And I didn't remind you, remember, if you find the intersection, that's the second trace 5. Enter. Okay. Did anybody get that? The second intersection point other than Carolina? Natalie? 4.76. Now, we already said that the x values, those represent what? The volume represented the y represented the volume. The x is representing the what? No. If only they labeled the axis for us. The height, okay? So those are the two different heights that's going to give us a volume of 100. Okay, so I can come down here. H equals 0.54. And the height of the other one equals 4.76. Now, did the problem just ask us for the height? No, what did they ask us for? The dimension. So we need to find the width and the length of each one. Now, whenever, at the very beginning, whenever we were talking about it, and this is the equation that you should have put in, okay, we said that the 12 minus 2x, that represented the width. And I told you that whenever I was kind of explaining the whole scenario, that if we have the height, we can find the other two, correct? Because they're both in terms of height. So, to find my width, I can take my height, put it in for that x, which I know the equation was h, but we put this in. I can put 0.54 just in this part of the equation. 12 minus 2 times 0.54 to get my width. And then I can put 0.54 in for this x of that part of the equation to get the length. And then I would do the same thing with 4.76 to get the width and length of that planar box. Okay, so on the planar box that had a height of 0.54, you should have gotten that the width was 10.92, and Lizelle, we were just saying that the length was what on that? 16.92. Okay, and then Jillian, whenever I put 4.76 in to find the width, what would that give me? Hadn't gotten there. Has anybody gotten that? What? No, you're going to take 4.76 now. So 12 minus 2 times 4.76, 2.48. And then I do 18 minus 2 times 4.76, 8.48. Okay. Now, let's talk about this other one that we've already determined would not make sense. But let's talk about it and why exactly it would not make sense. Okay, so if I find that the far x or the far intersection, that would give me a height, my x value of 9.7. So then if I took that and I tried to find my width the way that we just did, so I'd put 9.7 in there. That's going to tell me that the width is negative 7.4. Does that make sense? Can I have a negative width? No. Okay, so that is a reason as to why that would not make sense. Alright, let's go to the back. We're going to talk about these power functions, and by power functions, and it's just x to the power of a positive number. Okay, x to the second, to the third, to the fourth. So just how is it changing the graphs as that exponent increases? Okay, whenever we're talking about the end behavior of a graph of a function is the behavior of the graph as x approaches infinity and negative infinity. What you really need to pay attention to is if you're on the line and if you went to the left, is it going up or down? If you went to the right, is it going up or down? So this one is going which two directions? Down and up. Okay, down and up. X squared is going which two directions? Up and up. X cubed. Zach, x to the fourth. Hannah, Ray, x to the fifth.
Down and up.
Abby, x to the sixth.
Up and up.
Okay, pretty difficult stuff here. What is making the graphs either going in opposite directions or going the same directions? And I mean, obviously it's the exponents because that's the only thing that's changing, but what about the exponents? Do what? They're all positive, but what is giving me one that goes down and up as opposed to up and up?
The even numbers go up and up, and the odd numbers go down and up.
Okay, all of the ones that are up and up, x squared, x to the fourth, x to the sixth, those are all even. All of the odd degree, okay, the odd exponents are going down and up. Alright, so we need to make sure that we're aware of a couple other things as well on these. If you have an even degree, okay, and we'll talk about that terminology a lot more in this unit. It's just that exponent. If you have an even degree, on these examples they are symmetric about the y-axis. Okay. Now that can change if it moves, okay, but it's just other ones, they can be symmetric around other vertical lines. We saw a lot of that in quadratics. If it is an odd degree, the examples that we have here, those are all symmetric about the origin. But again, if it's moved, they can be symmetric around any one point. So make sure you get those two little notes written about that. And then talking about end behavior. So this goes along with the up and down stuff that we just talked about. Now we're going to draw a couple little pictures on each side, and I'll explain it. But if you have an odd degree power function and a is greater than 0, that means it did not reflect across the x-axis. Alright, it's going to start off going down, it's going to go up. Something's going to happen in the middle of the graph, and then it's going to end up going that way. If it is reflected across the x-axis, as it goes to the left, it'll be going up, and then eventually, and then as it goes to the right, it's going to go down. Okay, some examples of graphs that we'll see, and these are both these are extreme graphs here, but all right. So what that little cloud is representing is all this stuff in here. When I'm talking about my end behavior, I do not care about all of the up and down in the middle of the graph. Okay, the end behavior, so think big picture. As it goes to the left, it's going down to negative infinity. And then it's going to go up. It's going to, as it goes to the right, it's going to go up to positive infinity. So your even degree. All right. Easiest one to think about this is think about a parabola. Okay, it goes down, and then it ends up going back up. Whenever we get into those higher degrees, you can see stuff that's going to look like that. I don't care about all that down there. I care about where it started from and where it ends. And then if it's reflected, it does that. So next we're going to write the end behaviors of all these. You need to know how it's written, how to recognize it. And it's pretty convenient because everything will always be the same except for the last part of it. Okay, but how it is written and how it is read, as x approaches infinity, which in my mind, I think on the x-axis is infinity to the right or to the left? To the what? To the right. So in my mind, I think as the graph moves to the right, does it go up or down? Okay? Or as x approaches infinity, y approaches, on this one, if I go to the right, does it end up going up or down? Up. So is that positive or negative infinity? As x approaches negative infinity, or as x goes to the left, would this end up going up or down? Down. So y approaches negative infinity. Now I said a big part of this will always be the same. The part of this that will always be the same is that right there. Oh, sorry. On the odd degree when a is negative, as x approaches infinity, is y approaching negative or positive infinity? Negative, because it's going down, correct? As x approaches negative infinity, y is approaching what? Positive infinity. Going to the even degree when a is positive. As x approaches positive infinity, y approaches positive infinity. As x approaches negative infinity, y approaches what? Is it going up or down? As x goes to the left, y goes up. Even degree when a is negative. As x approaches infinity, or as the graph moves to the right, is it going up or down? Down. So that would be negative infinity. As x goes to the left, y goes up or down?